Good day to you. In previous segments, we've been discussing the relationship between the fundamental property of momentum and force and how that helps us relate work to energy. What I'd like to do now is to carry on our conversations about momentum and lead us into one of the fundamental laws of matter and motion, namely that momentum is a so-called conserved quantity. This is related to the first law of thermodynamics, which says that matter can be neither, that matter or energy can be neither created nor destroyed. And one of the implications of that is that because energy is related to momentum in a fundamental way, if energy is conserved, then momentum must be conserved as well. Now, let's come back to our demonstration of what momentum is. You have a mass of something. It has a center to it. You have it operating or moving under whatever influence at a particular velocity, and it has a mass, and that's going to have a momentum of mass times velocity. Now, we want to see how this relates to other bodies that are similar in mass or shape or what have you, how this relates to other bodies. And so what we're going to do is we're going to define this as body 1. And so what we're really referring to is the momentum of body 1, which is the product of body 1's mass and body 1's velocity. All right. Now let's draw another mass, and let's just pretend that they're both equal, and we'll call this mass 2 over there, and that's operating in some, moving in some velocity, and that's going to be indicated, as we said earlier, by a vector. Velocity has not only speed, but it also has direction. And so the velocity of particle 2 is going to be opposite in direction to particle 1. We can define a momentum for particle 2, and that's quite simple. Particle 2 is equal to the mass of the second particle times the velocity of the second particle. Now let's pretend for the moment that the mass of the two particles is the same, and that the speed, I'm choosing that word carefully, that the speed of both particles is the same, but they're traveling in exactly opposite directions to one another. They're about to have a head-on collision. What we can say here, we can define not only the momentum of each individual particles, but we can define the two particles as a system and calculate the total momentum of the system. And the total momentum of the system is going to equal the momentum of particle 1 plus the momentum of particle 2. Now, let's pretend, as I said, that the speed of both is the same, that the mass of both particles is the same, but the directions are exactly opposite to one another. What we can say then is that V1 is actually equal to the negative of V2. If we define this direction as a positive direction, we must therefore define this direction as the negative direction. And so what we have here is that the momentum of the system is equal to P1 plus minus P2. And if the mass of those two particles are the same, and the speeds of the two particles are the same, but opposite in direction, you have a momentum added to the negative of the same momentum, and the total momentum of this system is 0. Okay, now conservation of momentum principle says that in that system, momentum will be conserved, that is, it will not change at all. This does not mean that the velocity or the pattern of motion will change, but what it does say is that the momentum of the total system will remain the same. So let's take our hypothetical example. We have a mass going at a velocity in one direction. We have an identical mass going in the opposite direction. And we're going to say that the momentum of that system is equal to 0. Now note that both of these particles are moving. They both have individually momentum, but the momentum of one cancels out the momentum of the other, so that the momentum of the system is zero. Now when they finally collide with one another, their velocities are going to be zero. If the velocities are zero, then the total momentum of the system is also zero. Momentum is mass times velocity. Zero velocity, no momentum. But then if you have a perfectly elastic collision, as it's called, that is, no energy is lost from this collision, the momentum in here, in these two individual bodies, is going to be conserved, and those are going to manifest themselves a short time later as a recoil of the two particles against one another. And now the velocity of this particle is going to be going in the opposite direction that it was before, and the velocity of this particle is going to be going in the opposite direction that it was before. And if all the energy is conserved in here, the momentum of the system is still going to be zero. In other words, in this system, even though the momentum of individual particles change, when they engage in a collision, the momentum doesn't go away. It comes out manifesting itself in another form, basically moving particles in a different velocity, but the total momentum of the system in this instance is the same. Okay, let's have a practical demonstration of this. And we can do this quite simply with a couple of coins. There's our nickel, and let's take a quarter, and let's take another quarter. And what we're going to be doing is we're going to be doing a little experiment where we're going to impart momentum from one coin to another, and we're going to see how the system is conserved. This is a trick that we've all done. We can hold this coin down right here, the nickel, and we're going to take the quarter, and we're going to very, very carefully accelerate this towards the nickel and make the quarter move. Let's do that again. Okay, now you see that the quarter did not move very far in this case. Now that's an instance where momentum in this system was conserved, and let's analyze for a moment how that actually worked. Here's our quarter, here's our nickel, and here's our quarter. Initially, this quarter had a certain momentum. When the quarter impacted the nickel, you had a wave of elastic recoil that spread through the nickel and imparted momentum to the other quarter. And when that momentum was imparted to it, the quarter recoiled from the coin. Let's look at what's happening in a bit more detail. And let's take the edge of the quarter that's accelerating towards the nickel. That's accelerating towards the nickel with a certain momentum. When it encounters the nickel is a crystalline metal. All the atoms in there are held together by strong covalent bonds, and we can formulate a chain of these molecules, or these metal atoms, that are hooked to one another by these covalent bonds to the other quarter over here. And what happens when the first quarter impacts the nickel? The momentum doesn't go away. The momentum is instead imparted to accelerating the atoms close to the surface or close to the edge of the nickel. That in turn imparts momentum to whatever is connected to it, which in turn imparts momentum to whatever is connected to it, and so forth and so on, until finally the momentum comes out the other side and imparts momentum to this quarter over here. So in this instance, you've had a conservation of momentum in every instance, and showed up as a kind of motion of matter. The motion of all the atoms in the quarter on this end, conveyed to motion of individual atoms as a wave of compression spreads through the nickel, and finally that's imparted to the quarter on the other side, accelerating it. We also remember that momentum is the product of mass times velocity, and we should be able to demonstrate that here. Now, if you just do a quick Google search, you can find out that these coins have quite different weights. And so, for example, a quarter weighs about 5.7 grams. A nickel, on the other hand, weighs about 5 grams, about the same as the quarter. And a dime weighs 2.3 grams. So the weight of a quarter is about twice the weight or the mass of the the nickel. Sorry, the mass of the quarter. So we should be able to demonstrate conservation of momentum simply by seeing if the quarter or the dime are accelerated more, that is have greater velocity than is the case for the other coin. So let's take our quarter. And we have to be very careful here. This is a very imprecise thing, but we will start to accelerate it, and we see that the quarter moves that much. Let's try it again. Let's try it yet again. Okay, so it's moved that much. Let's move the nickel down now and try to do the same thing with the dime. And it's just shot right off. Now, I'm not sure if we were able to catch that on video, but let's try it again. It not only goes further, but it goes faster. Now, this is a perfectly sensible thing for these quarters to do, for these coins to do, because after all, what is momentum? Momentum is equal to mass times velocity. If you have a given quantity of motion, that is a given momentum of the first quarter, that is the quarter that's accelerating towards the nickel, that momentum is going to emerge on the other end as a product of mass times velocity of the other coin. If the other coin is a quarter, the momentum in the quarter will come out as a velocity that's identical to the velocity of the quarter coming in. On the other hand, if you have a dime which weighs about half, this mass right here is half. That means that the velocity that emerges from the momentum imparted to it by that moving quarter is going to be about twice that of the quarter. So let's demonstrate it one more time. We take our quarter, we take our nickel, we take a quarter, and we try to, let's do that again, we try to impart momentum to that. The quarter has gone this far. Let's take our dime. Right off. Okay, so it's very simple to demonstrate conservation of mass in these very simple systems. In some other videos, we will be talking about conservation of momentum and energy in other kinds of contexts, but the fundamental lesson remains the same. Momentum is a conserved quantity. It doesn't go away, it can't be destroyed, it can't be conjured out of nowhere. If you have momentum, that means it had to have come from somewhere, and in any kind of interaction between bodies, you have to be able to account for all the momentum. And when we come back in another video, we'll see some of these other contexts in action. Well, that's all for now, and we'll see you later.